Our first presentation will be given by Jonathan Dumas, who is a PhD student at the University of Liège in my group. Jonathan graduated from École Polytechnique in France and worked in the power system industry for a while. And then he's now working on energy management in microgrids, including forecast uncertainty and energy transition aspects. So Jonathan, please, you can share your presentation. And
thank you, Bertrand.
Yes, thank you.
And I cannot share my screen, in fact.
Can you do that now?
No. Ah, okay. Okay, great. Can you see my screen?
Yes.
Okay, great. So yes. Thank you, Bertrand, and good evening, everybody. So I am very pleased to present you the paper, Coordination of Operational Planning and Real-Time Optimization in Microgrids. So this paper focuses on the tertiary control level with the energy management system that aims to compute optimally a planning of set points to the microgrid device based on economic and technical criteria. More specifically, a two-layer approach is considered to address this task. It consists in a schedule and a dispatch layers. The dispatch layer computes on a quarterly basis an economical operation scheme for the 24 hours ahead with a 15-minute resolution. The dispatch layer computes the set point in real times based on the scheme and the microgrid status. The key question is how interact the schedule and dispatch layer. This topic has been intensively studied in the literature. So first we'll go with the problem formulation. So the problem formulation can be defined for a given microgrid design and configuration as operating a microgrid safely and in an economically efficient manner by harvesting as much as renewable energy as possible, operating the grid efficiently, optimizing the service to the demand side, and optimizing other side goals. So we made a few assumptions in this paper. First, the controller optimizes economical criteria, which are only related to active power. Secondly, fast load frequency control, islanding management, as well as reactive power control are not in the scope of the study. Thirdly, the battery aging is not taken into account and is supposed to behave ideally with charging and discharging efficiencies. Finally, the microgrid is a price taker in the energy and reserve markets. So here you can see the abstract formulation of the microgrid control that is provided by equation 1. AT is a set of action at any time t over the lifetime of the microgrid. The action should be taken as frequently as possible to cope with the economical impact of the variability of the demand and generation size, but not too often to let transient vanish. Typically, a few seconds is fine. Delta t is the time delta between action and is not necessarily constant. And some of the actions are purely market related. They are denoted with A superscript M, while others actions are communicated as set points to the device of the microgrid, A superscript D. The state S of the microgrid is also made of two parts. S superscript D that represents the state of the device, such as the state of charge of the storage system, for instance, or the state of a flexible load, while S superscript M gathers information related to the current market position, such as, for instance, the nominated net position of the microgrid over the next market periods. C is the cost function that gathers all the economical criteria considered. And finally, F is a transition function that describes the physical and net position evolution of the system. This problem is quite difficult to solve since the evolution of the system is uncertain, actions have long-term consequences, and are both discrete and continuous. So now let's switch to the proposed method. As forecast as valid only for relatively near future and optimizing over a long time horizon would anyway be incompatible with real-time operation, this problem is approximated by cropping the look-ahead horizon to 24 hours. However, market decision must be refreshed much less frequently than set points. We thus propose to decompose the problem in an operational planning problem that computes every 15 minutes market decision and the value function for the 24-hour ahead, and a real-time problem that computes every few seconds set points based on the value function and the microgrid status. The real-time optimizer computes only set points within the current market period. So we consider only one period for the real-time problem. Figure 2 illustrates this process. This value function propagates the information from the operational planner to the real-time controller. Therefore, equation 1 is decomposed into equation 2 and 3. And the value function represents the optimized value of 2 as a function of a state of charge of the problem. And if we make the assumption that equation 2 is modeled as a linear program, this value function is thus convex and piecewise linear. The objective of the operational planner is composed of immediate and delayed costs. The immediate costs take into account different revenue and costs related to energy flows, the cost of share demand, steer and non-steer generation, the revenue from selling energy to the grid, the cost of purchasing energy from the grid, and the cost for using the storage. The delay costs are composed of the peak cost and symmetric reserve revenue. Delta P is the peak difference between the previous maximum historic peak and the current peak within the market period. The symmetric reserve is provided to the grid within the current market period. The objective function of the real-time controller is composed also of immediate and delay cost and the value function. The real-time optimizer immediate cost are the same as the operational planner immediate cost by replacing time index and replacing delta 2 by delta t and considering only one period of time. The real-time optimizer delay cost is composed of the peak cost and symmetric reserve penalty cost. Every evaluation of the objective of the planner with a fixed state of charge at the end of the first market period, and provide us a supporting inequality by taking the dual variable that is called mu. Thus, the value function is approximated by a set of cuts or inequality. It is like a parametrization of the right-hand side of the objective of the planner, in fact. So by this way, we can approximate the value function. Okay, let's consider now the case study. The PV and consumption data have a 1 second resolution, meaning that the real-time controller could compute its optimization problem each 5 to 10 seconds in operational mode. And thus, we consider the case study of the MIRIS microgrid. It is located at the John Cockerill Group's international headquarters in Belgium. It is composed of PV, several energy storage devices, and a non-shadable load. The load and PV data we use come from on-site monitoring, 27 days in total. All data, including the weather forecast, are available on the Kaggle platform. You have the link here. Figure 3 illustrates the PV and consumption on a specific day, June 12, 2019. The case study consists in comparing the two-layer approach, named RTO-OP, to a rule-based controller for free configuration of the installed PV capacity, as shown by Table 1, where the PV installed capacity increases from 400 kilowatt to 1,750. All the other parameters are identical for the free configuration. The selling price is constant, 35 € per megawatt, and the purchasing price is composed of a constant day and night prices, 200 and 120 € per megawatt. The peak mechanism is taken into account with a constant peak price that is set to 40 € per kilowatt and an initial maximum historic peak of 150 kilowatts. Storage systems are initially fully charged, and the battery capacity is set to 1,350 kilowatts. The operational planner computes the planning based on PV and consumption 24 hours ahead, based on 24-hour ahead forecast. The computation time of the real-time controller on a regular computer is around a few seconds, and the operational planner around 20 seconds. So in total, the simulation computation time is up to a few hours when considering the entire dataset. The weather-based forecast methodology consists in two classic deterministic techniques: a recurrent neural network that is implemented with the Keras Python library, and a gradient boosting regression that is implemented with the scikit-learn Python library. This model uses as input the weather forecast provided by the Laboratory of Climatology at the University of Liège. To estimate the impact of the PV and consumption forecast error of the controller, the simulation is performed with the planner having access to the PV and consumption future value. So here we have the result by considering the peak management without symmetric reserve. The peak cost strongly penalizes the benefits as it applies on all the year ahead once it has been reached. When the planner uses perfect forecast, it provides the minimal peak cost, whereas the rule-based controller provides the minimal energy cost on all the cases. However, the perfect planner achieves the minimal total cost composed of the energy and peak cost. That is expected because it is an oracle, it knows perfectly the future. The simulation illustrates the impact of the forecast on the RTOOP behavior. The RNN forecaster provides the best result, but is still a long way to manage the peak as the oracle due to the forecasting error. These cases show that the RTOOP controller optimizes PV storage usage and thus require less installed PV capacity for a given demand level. This result was expected as the peak management is not achieved by the rule-based controller and becomes critical when the PV production is smaller than the consumption. Now let's consider the numerical result when we set the symmetric reserve. So here, the price of the symmetric reserve is set to 20 euro per kilowatt. And as you can see, the RTOOP tends to maintain a storage level that allows it to better cope with a forecast error, as we will see on the next slide. So here we only consider the RTOOP with the RNN forecaster, and you can compare the results with symmetric and without symmetric reserve. The peak power has decreased on all cases. However, this behavior tends to increase the energy cost if the PV production is important in comparison with the consumption, such as for case 3. Indeed, the controller will tend to store more energy into the battery instead of exporting. That is why there is an economic trade-off to manage the peak and the reserve simultaneously, depending on the valorization or not on the market of the symmetric reserve. The reserve can also be valorized internally to cope with known or difficult forecastable events, such as a sudden drop of the export or import limits due to loss of equipment or grid congestion. So this case study was just to illustrate the two-layer approach, but it could be used for other kind of application. So we have seen that the value function computed by the operational planner based on PV and consumption forecasts allows to cope with the forecasting uncertainties. The real-time controller solves an entire optimization problem, including the future information propagated by the value function. This approach has been tested on the Meris microgrid case study with PV and consumption data monitored on site. The results demonstrate the efficiency of this method to manage the peak consumption in comparison with the rule-based controller. This test case is completely reproducible as all the data used are open, PV consumption monitored, and forecast, including the weather forecasts that are available on the Kaggle platform. The proposed approach can be extended in several ways. First, the deterministic formulation of the operational planning problem could be extended to a stochastic formulation or robust formulation in order to cope with probabilistic forecasts. Secondly, the balancing market mechanism could be introduced. Finally, the approach could be extended to a community by considering several entities inside the microgrid. And then we could introduce kind of green KPI, key performance indicator, to try to meet the challenges of the IPCC reports. So I would like to thank you for your attention, and I would be very pleased to take some questions.
So thank you, Jonathan. Please do not hesitate to ask your questions in the Q&A. Okay, we have a first question, Jonathan. I think you see the questions. Maybe yes. I can read it. It's from Jordan Olweger. So why using neural network for forecasting PV if you already have weather forecast? Yeah, this is
okay.
a question. Right.
Yes, it is true that as we have weather forecast, so yes, we have the global solar irradiation, and we also have the air temperature. So we could use a parametric model with the parametric law to directly compute the PV power. But by using a neural network, you can take the last measured value of the PV production. And so you can increase your forecast accuracy by taking the last state of the system. So it is a way to improve the forecast accuracy. And also the recurrent neural network has a specific time gate inside it. So it is quite powerful when you take information in the past. So this is why we decided to use such a machine learning approach instead of a parametric model. I hope it answers the question.
Thank you, Jonathan. Then you have a follow-up question. How often do you train your neural network to update it with past value?
Yeah, okay, good question. Thank you for the question. So in fact, when we decided to implement this algorithm on site, we decided to update the neural network every 6 hours. And it's trained on 2 weeks of data, dependent on the case, but 2 weeks or 1 week of data. So every 6 hours, the neural network is retrained with the last week or the last 2 weeks of data. And the training is quite fast, so it takes only a few minutes. So we didn't decide to use transfer learning as it was quite fast to do it.
Thank you, Jonathan. Any other question from the audience? Okay, maybe I can ask a little question. Oh, yeah.
Yes.
So, Jonathan, how do you think the approach could be extended if we have non-convex dynamics, or if we have, for instance, a planning problem, which is a mixed integer program, or if we have something like that?
Yes, that is a good question, because here we did not include, for instance, the aging of the battery, and the transition function is not non-convex because we consider a very simple one, but it could be completely different, especially if we included a more difficult transition function to measure the battery or the aging of the battery, or I don't know, something else. So there are several techniques that could be used. First, we could try to linearize the problem by using some tricks, but sometimes it is not possible. So maybe it would be, if the problem it cannot be linearized, maybe we could use a kind of Bender approach to decompose the problem in 2 parts with a master problem that could be a linear problem, and where we could put some of the binary variable, for instance, to have a mixed integer linear problem. And into the subproblem, try to have a linear problem, but if it is not a linear problem, it can be a quadratic problem or maybe a nonlinear program, then we may try to address this subproblem with another approach by trying to bound it with an upper bound and a lower bound, and until to reach a convergence.
Okay, thank you, Jonathan. So I think time is up.